So we talked a little bit about the origin of magnetic fields, and I want to talk about the relationship between magnetic field and electrical currents. Just a simple example that most people probably did in middle school or elementary schools. If you take a metal bolt that is not magnetic at all, this doesn't pick up paper clips or stick to anything magnetic, and wrap it around with wire, and then have an electrical current flow through that wire just by connecting it to the two ends of a battery. Even a small amount of electrical current will cause this to be magnetized. If I turn the current off, actually the bolt stays magnetized a little bit, but magnetism quickly dissipates. If I connect it back up together again, okay, it becomes magnetic. So we can see that the electrical current flowing through this circuit is what is causing that magnetism, not the permanent magnetism of this metal. So the relationship between moving electrical charges and magnetic fields is well established. If you think about this in the context of a permanent magnet that is able to generate a magnetic field, what that means is if magnetic fields are only due to moving electrical charges, there must be somehow moving electrical charges inside of this electromagnet, this permanent magnet, which at the atomic scale involves electrons that are moving around the nucleus of an atom, and that motion of an electrical charge constitutes an electrical current, and each one of those electrons generates a little tiny magnetic field. The peculiar characteristics of certain metals, which allows the magnetic fields of many of those individual atoms to line themselves up, is not something we're going to talk much about or concern ourselves with in this course. But suffice it to say that if you want evidence that there are electrons moving around inside of atoms, the very existence of permanent magnets, whether it's a manufactured permanent magnet or a natural permanent magnet, like we can find certain rocks with certain metal compositions that solidified in the Earth's magnetic field retain that permanent magnetism. That's evidence that there are electrical charges in some sense moving around inside of there. Even an individual electron, which in modern physics is regarded as a point particle, a sort of zero-dimensional Euclidean point, has got a magnetic field, has got a magnetic dipole moment due to the fact that it is electrically charged and it has angular momentum, what's called spin in particle physics. Even though you might ask, well, if an electron is a zero-dimensional Euclidean point, how can it spin? It doesn't really spin in the sense that a ball or something spins around an axis, but it carries angular momentum, and because it has angular momentum and charge, it has a molecular or a magnetic dipole moment. It actually has, it acts like a tiny magnet when placed in a magnetic field. So even at the level of individual particles, there is magnetism associated with electrical charges and velocity or momentum. I want to talk a little bit about just the relationship between electrical current and magnetic fields. If you've got a wire that is carrying a current I, the equation which tells us how much magnetic field is generated by that current is called Ampere's Law. And Ampere's Law says that, well, I'll just write it out for you, that the magnetic field integrated around a loop is equal to mu zero, which is the magnetic cousin to epsilon zero. This is the magnetic permeability of free space times the current. There is no real magnetic analog to Coulomb's law because there's no such thing as a magnetic north or south pole that lives apart from that lives isolated, that creates a force field or a field, a monopole field. So the equation that's considered the fundamental equation of magnetism is this law, which is Ampere's law, sometimes called Ampere's circuital law. Ampere's law tells us that if we integrate the magnetic field around a closed loop through space, if there is current passing through that loop, then the integral of B around that loop will be equal to the current passing through that loop times mu zero. It is the magnetic analog to Gauss's law. Remember, Gauss's law says if you've got electrical charge enclosed by a surface, that the integral of E dot dA is equal to the Q enclosed over epsilon naught. That's Gauss's law. Ampere's law for magnetism says the integral of B, the magnetic field around any closed loop, is equal to mu zero times the current through that loop. It is true for any path, just like Gauss's law is true for any path, that the magnetic field integrated around that loop is going to be equal to mu zero times the current through that loop. But just like Gauss's law was only particularly useful in situations where the symmetry of the problem allowed us to calculate something, Ampere's law is also only going to be particularly useful with arrangements of current and choices of loops that make this integral something that one can do. The simplest example is, suppose you've got a current just going up the z-axis, say, in a cylindrical coordinate system, and you make a circular loop of radius r around that loop. We should be able to guess from the symmetry of the situation that B anywhere on this loop has got to be constant. Okay? B can't be a function of R because the problem is symmetric with respect to, well, let me say it this way. B can't depend on theta here because the wire looks the same no matter where you are in theta. It can't depend on Z if the line of current is considered infinite, because it doesn't matter where you are in Z, or if that line is infinite, nothing about the problem changes. The only thing it can depend on is R, so I can write B is equal to B of R. And hopefully we can see that it also doesn't have any, well, we'll leave it at that. That B is just a function of R, and that it's constant everywhere if R remains constant. So everywhere in a loop of constant radius, B is going to be the same. So when I write Ampere's law, the integral of B dot dl around some closed loop is equal to mu zero I. In this case, the current through the loop is just what I've labeled I. The integral of B dot dl, if B is constant everywhere on this loop, that's just B times the length of the loop. So that's B times 2 pi r equals mu zero I. And this gives us a very simple equation for the magnetic field due to a loop of a wire, and that's B is equal to mu zero over 2 pi times I. So that's the magnetic field due to a loop of wire. What's the direction of the magnetic field? Well, if I is going to have a positive current in this direction, and we go around our loop in this direction, this dot product, they're 90 degrees, so that dot product just gives plus 1. The convention for the direction of the magnetic field due to a wire again uses the right-hand rule. If you put your thumb in the direction of the current, the direction that the magnetic field goes around that wire is the direction that your fingers curl. So in this case, the magnetic field of the wire goes around in this direction, around that way, around that way, around that way. Okay, so the magnetic field of a wire wraps around the wire like so. If I draw a picture of a long straight wire, some of this is hard to get across in 2 dimensions, but if I've got some wire carrying a current I, the magnetic field wraps around the wire this way. So behind, in front, behind, in front, behind, in front. And it's constant with respect to Z, and it depends on R. So as you get further from the wire, the magnetic field gets weaker and weaker and weaker. So B is proportional to 1 over R, which shouldn't be surprising. We said that things that are move away from a point source generally follow 1 over R squared law. Things that move away from a line source generally follow a 1 over R law. And things that move away from a plane source are generally constant. So that's Ampere's law. That is an example of how you use it. The next thing that your book does is example 28-6, finding the magnetic field inside of a current carrying wire of radius capital R. Very similar to the problem we did in the Gauss's law chapter of finding the electric field inside of a cylindrical conductor. So go through example 28-6, and see if you can follow along with that derivation. It's relatively straightforward. The next example that your book talks about is the magnetic field of what's called a solenoid. So I'll make a separate video, or I'll pause this video and continue on talking about the magnetic field of a solenoid, because those are really, really important. A solenoid is just a coil of wire. When I gave the we're going to use this example of a magnetic field a lot when we talk about magnetic induction. So we'll go through this. And then in section 28-6, your book talks about the law of Biot-Savart. We probably will not actually solve any problems using the Biot-Savart law. They're pretty tricky and complicated. It's very similar to directly integrating to find electric fields, but because the form of the equation is a little bit different, and it depends on little bits of current, not little bits of charge. Biot-Savart problems are actually a little bit trickier. So I might do 1 or 2 of these as an optional example, but I'm not going to assign any problems from 28-6, the Biot-Savart law. So we'll talk about solenoids really, really briefly, and then we'll move on to talk about magnetic induction. So looking at section 28-5 in your book, this is a solenoid. A solenoid is just a coil of wire, just wrapped around and around and around and around, that's hollow in the center. So this particular coil of wire, it says on, if you look at it has a resistance of 62 ohms. It's got 3,400 turns. So there's a thin little wire that's wrapped around this plastic frame 3,400 times with a hole in the middle. And what we want to answer is the question, if we run an electric current through this coil of wire, what will the magnetic field be in the middle? And so we're going to use Ampere's law to determine that. Sorry, my mic was a little bit far away from me there. Hopefully you could all hear that. So let's take a look at what this looks like mathematically. If we draw a cross-section of the solenoid, so the cylinder is sort of wrapped this way, and we've got current going around that loop. So say at the top of the solenoid, the magnetic field is coming out of the page. And then it wraps around, and at the bottom it's going into the page. Okay, so this is a cross-section. If we sliced the solenoid lengthwise and just looked at a single plane of that solenoid cut in half. Okay, so the wire is cut in half so that at the bottom of the page, the magnetic field is going into the page, and at the top of the loop, it's coming out. And I want to know, what is the magnetic field inside here? If I know the current, and I know Ampere's law, which says the integral of the magnetic field around any closed loop is equal to mu 0 times the current. So let's say the total current flowing through this wire is I. I goes in here, I comes out there. What loop do we draw in order to have a sort of sensible thing that we can calculate using Ampere's law? This isn't obvious, but the loop that your book chooses is a rectangular loop like this. Actually, your book does the arrows this way, like this. That encompasses just part of the coils, and that is infinitesimally thin this way, perpendicular to the surface of the cylinder that defines the solenoid. So we know that from Ampere's law, the integral of B dot dl is equal to mu 0 I. And the current through our little loop here is just equal to the current I times the number of loops. I can't call that capital N. Well, sure I can. The number of loops that go through my surface here. What is the direction of the magnetic field? If the current is into the paper, okay, the right-hand rule tells me that the magnetic field due to this loop is around this way, and this loop is around that way, and this loop is around that way, and this loop is around that way. So this may be hard to see. Maybe I should draw an expanded view of it down here. Okay, so the current is going in. This current creates a magnetic field that goes around this way, according to the right-hand rule. This current creates a magnetic field that goes around this way, according to the right-hand rule. This goes around this way. This goes around this way. So the direction of the magnetic field wraps around these coils. If these coils are very close together, hopefully we can see that inside the solenoid, all the magnetic fields add together this way, and outside they all add together that way. So the integral of B dot dl, if B is just constant along this line here and constant along this line here, is just going to be equal to the magnetic field times this length L of our loop. Now our loop that we chose is just arbitrary, but we know that B times L is going to be equal to mu 0 times I times the number of wires that comes through the loop that we chose. So the magnetic field is just going to be equal to mu 0 times I times, your book calls this lowercase n. Lowercase n is the number of turns per unit length, n over L. So we bring our L over here. We've got B equals mu 0 I n over L. We call n over L little n. So the magnetic field inside of a solenoid, just inside of the turns, is going to be equal to the magnetic constant times the current times the number of turns per unit length. No, that's not right. Yeah, that is right. B is equal to mu 0 I, that's equation 28-4. And what your book points out next is that the magnetic field depends on where you are inside the solenoid. It doesn't depend on the length of the solenoid. And so a solenoid is actually a way to create a uniform or a relatively uniform magnetic field. When you build a large solenoid and you have current flowing around the solenoid, at some point inside that solenoid, if I put my solenoid on the floor, hold up. Okay. If I take this large solenoid and I pick some point here in the center, the magnetic field is roughly constant in the center of the solenoid. If we were doing a lab, we actually have magnetic field meters. We could run some current through this and measure how much the magnetic field varies as a function of distance from the coils. It's a little bit complicated because the coils here obviously have finite width. But what matters is the number of coils per unit length, the density of the coils, because the denser the coils are, the more current is flowing through each wire, the more current flows through our little Ampere circuit, the little arbitrary loop that we chose. Okay, so that's Ampere's circuital law and how you find the magnetic field of a solenoid. By the way, once you make the whole solenoid, you can use the right-hand rule to tell the direction of the magnetic field. In this case, let me draw this. Again, a sort of cross-sectional, zoomed-in view of this. You've got a solenoid. This is a cutaway of just a few of the wires. Let's say the current is going this way. So it's in up here. It's out down here. If you look at the individual loops, use the right-hand rule for the individual loops. Here, the individual loops are going in. So the right-hand rule says the current's wrapping around this way, which means inside the wire, or inside the solenoid, sorry, the current is always pointing that way. Here, on this side of the solenoid, the current's coming out, so the magnetic field wraps around right-hand rule, okay, like this. You notice on this side also, the magnetic field is going this way. So the magnetic field inside of a solenoid points like that. If you think about the solenoid as a whole, we can use a different version of the right-hand rule to determine the direction of the magnetic field of the solenoid. In this version of the right-hand rule, your fingers represent the current. You wrap your fingers in the direction that the current is going, and then your thumb points in the direction of the magnetic field. So here the current is going out, in, out, in, out, in, like this, and your thumb points in the direction of the magnetic field of the solenoid. So for a solenoid or a loop of current, you put your fingers in the direction of the current, okay, and your thumb tells you the direction of the magnetic field. Okay, so that's a slightly different application of the right-hand rule for finding the direction of the magnetic field of a current loop or a solenoid in the inside, in the center. I goes in the direction of the current. B is the direction of your thumb. There's a little table somewhere in the chapter that shows you all the different flavors of the right-hand rule that you use when dealing with magnetism. Okay, so there's this version for finding the magnetic field of a loop or a solenoid, and then for a straight wire, you put your thumb in the direction of the current, and then the direction of your fingers tells you the direction of the magnetic field. Okay, so that's two slightly different right-hand rules for two slightly different things, and then there's the QV cross B right-hand rule for finding the direction of the force on an individual charge in a magnetic field. Where is that table? I know it's in here somewhere. I'll find it. I'll post it. Oh, here it is. Summary of right-hand rules is page 716. Right-hand rule. Well, I'll just do this. Okay. Right-hand rule. Magnetic field produced by a current. Force on an electric field due to a magnet, and force on an electric charge due to a magnetic field. The solenoid is in here, but we'll do that later. Okay, so here's a question. What other problems can you do with Ampere's circuital law other than a long wire and a solenoid? The answer is not a whole lot. Example 28-10 does a torus. A torus is just a solenoid that's wrapped around in a circle. There's not a whole lot more to say about it. So we will, maybe I'll do an example of the toroid, or I'll just ask you to read through example 28-10 yourself. Notice there's not a whole lot of calculating. So we'll see if we can do a couple of homework problems with Ampere's law, but I think that's really all we want to say about magnetism in terms of wires and charges. And then we want to get right onto magnetic induction, or the relationship between magnetic fields and changing magnetic fields and electrical currents, and the role that magnetic fields can play in an electrical circuit through a piece of electrical apparatus. I don't even know what to call it, a circuit element like a resistor or a capacitor called an inductor. And we'll talk about those probably next week.